Great. So my name is Aisha Forbes. I'm a first-year MBA candidate at Sloan. And here to present a open source workshop is Connor Heaton.
Thanks. Hi, everyone. Thank you for coming today. And thanks to the organizers, everybody, especially Dubum, for reaching out about the workshop. So I presented this work yesterday as part of the research paper competition, a more succinct version of it. But today I'm going to go into a little bit more depth and talk a bit more about the technical side of things. And if you guys have questions, willing to work towards that direction too. But so at a high level, what's the overview for what I will be talking about today? I'm going to start by giving a little bit of introduction for the work and motivating it. Probably don't need to spend too much time on that with this audience, but then after that, I'm going to introduce some of the recent work in machine learning that we take advantage of, specifically BERT, and then the idea of self-supervised contrastive learning. I'm going to describe our approach for describing player impact in the short term, which we call describing player form. And then I'm going to talk about our data collection and how we use that data to construct records to train our model, a bit about how we train our models, and then take a look at some of the code that I provide on the repository and the embeddings that the model produces, and then have some time for questions. And so my advisor and I come from a more NLP, natural language processing background, and so we're familiar with sports and interested in sports, but our sort of outside perspective, as it were, is that a lot of analysis and analytics are dependent on sort of just counting and rate statistics. And so I think that that's pretty easy to see for some of the more traditional statistics, maybe batting average or whip. It's pretty clear how you're counting two or more quantities and then dividing one by the other. But it's also prevalent in more advanced sabermetrics that I think have a bit of a more following in the community. WAR, for example, they do make some adjustments and try to tease some more useful signal out of that. But at the end of the day, the principal inputs are these. Pointer's not coming through too well, but the principal inputs are these counts of how often did a certain batter induce a home run or a walk, a double, what have you. And so I'm not trying to disparage WAR or anything. It's clearly useful to a lot of people, but I think there are some aspects of that in which can be improved. And so one example that I've talked to a couple of you about is so when you're computing WAR, you're computing the WAR for an individual player. All of the events are essentially the same. So a single is a single regardless of how it happened. And I think it'd be important to maybe tease out some more information about how that single happened. So was it a single on an infield hit where the batter beat the throw to first? Or was it maybe a ball hit to deep left where the batter only had the ability to make it to first when perhaps the majority of batters would have made it to second? And so it's still a single, it's still good, but maybe that's not as good of a single. And so that's maybe just like a shortcoming that we saw. And at the same time, there is these in-stadium sensor suites that do provide high-resolution information about the game being played. So a lot of people are familiar with Stackcast or PitchFX, and so that provides the information to provide the context to the type of single, for example, the speed, location over the plate of a pitch, the movement of the pitch, as well as how hard the ball was hit, where it was hit, what angle, what have you. So we really have this very high resolution sensor data describing the game, but a lot of things are sort of crude and the single, double, triple, what have you. And so a lot of people are working to provide more nuance, but we also took a crack at it. And so, I probably don't need to spend too much time on this, but, is this nuance important in identifying? I think it would be easy to make the argument, in the long term when you're computing WAR, the player that induces more doubles instead of singles is going to have, the player that converts those singles to doubles is going to have a higher WAR, and so, WAR is meant to sort of quantify the value of a player. So, in the long run, that's fine. But I think, especially with the legalization of sports betting, and, FanDuel just had the talk, I think this short-term evaluation is coming more into play. I think I only was able to catch the end of their talk, but they were saying, dealing with like momentum swings in games or something, it's hard to, quantify those sort of in-game events and the momentum swings and whatnot. And so we think, trying to, create a way of, at least computationally modeling the game in the shorter term will be, coming more into view in the, recent years, in the coming years. Oops. And so that essentially, culminates in our sort of motivation for working on this project was to construct rich descriptions of how players impact the game in the short term. And so one thing that we want to do, we know we want to do is, actually view the game as a sequence of events, a sequence of pitches, as opposed to just the, higher level, summary statistics describing the events. And we obviously want to take advantage of this in-stadium sensor data when we do that to provide that context to how these events happen. And then we want to create some sort of embedding that describes how the player has impacted the course of the game over a sequence of events or a sequence of plate appearances, for example. And so in order to do that, we take advantage of some recent work in the machine learning community. And so the first piece of work I want to introduce is called BERT. And so BERT stands for bidirectional encoder representation from transformers. And so that can be a lot, but the first part I want to highlight is the two middle words, the encoder representation, which kind of describe how BERT functions. You give BERT a piece of text, and then BERT processes the text and gives back to you an encoded representation of that text. It's like a 700 dimensional vector describing the text that it was given. And so that, sort of how BERT works. You give it text, it encodes it, and creates an embedding that is useful for, performing just language tasks related to that text. And so BERT is what is known as like a pre-trained language model. So it was pre-trained to perform two basic tasks that give it that sort of general understanding of language, from which it can be fine-tuned to perform specific language tasks. And it's been shown to provide state-of-the-art and a variety of language tasks, sentiment analysis, question answering, named entity recognition, what have you. And so, but I want to talk now about a bit about the pre-training procedure that BERT was trained with and what gave it, that starting point, that understanding of language as a sequence of words. And so it was trained using two tasks, but the first task that it was trained to perform was called masked language modeling. And so, during training, BERT was essentially asked to browse all of the Wikipedia pages, and the MLM objective basically accounts to fill in the blank questions. BERT was given, or BERT would randomly mask 15% of the words it was given, and then ask itself to predict what was missing. And it would try to, it would look at the context of the text, the context in which the mask was, in order to make that prediction. And so, when there's not a lot of context to go off of, such as that first example there, it's just I love you or I love blank. In this situation, there's not a lot of context. The model can probably just revert to very common sayings in the language. I love blank. I think a good bet at completing that would be I love you. It's pretty context agnostic. It's something that happens a lot in language, but when the model is given more context to work with, it becomes a harder task, and it needs to learn more about the language. So in the second blank, it says, let's go to the blank and swim. In order to fill in that blank correctly, BERT, kind of has to learn that that blank corresponds to a, some sort of location. You're going somewhere, some sort of noun maybe, and that it's related to swimming. And so over time, as BERT understands the language more and more, it'll start to realize that, okay, this candidate, or this blank, maybe the pool and the swim park and, maybe Kalahari or something are candidates, but over time, the model will learn that in this context, pool is maybe a good insertion there in that blank. And then for the third one, it's a similar story. There's a blank there, and the model needs to learn, or needs to look at the context to make sense of what that blank should be. And so this is a kind of a micro-based objective, how we view it, and where it teaches the model the rules of the language, so sort of maybe some grammar, things of that nature, as well as learning the role or the meaning of different words in the language. Learning the association that eating is something you do when you're starving, and when you go to the pool, you can swim, for example. And so it's a pretty simple task, but over time, the model learns a lot about English. And this task is paired with another, pretty simple task, which is next sentence prediction. And so it does these both at the same time. And the next sentence prediction task is basically when BERT is given two sentences, two random sentences from Wikipedia, and asked to predict if they follow one another, naturally or in the wild. And so just for some examples, so the first sentence is baseball is a game between two teams. One team wins, the other loses. And so in order to make these binary predictions, the model needs to understand, what is being expressed in those two sentences, and then make a judgment as to whether or not they kind of express similar sentiment. And so in this case, both sentences are sort of talking about the game of baseball, talking about teams competing. One team loses, one team wins. So it would make sense that those may appear together next to each other naturally. But then, for example, if we say, I went to the museum yesterday, and then the population of PA is 12.8 million. That's maybe not something you would really expect to see next to each other in the wild. And so maybe if it said the population of PA in 1915 was, X million, then that would be something that would be like a historical fact and something you learned at the museum. And so the model would be expected to then, in that case, say true. But here they seem pretty, divergent, so it would just say false. And so this task essentially complements the other task that focuses on individual words and what they mean, to encourage the model to look at the emergent meaning from a sequence of those words, for which it learned the meaning. So they complement each other pretty well there. And so what the model uses to make this next sentence prediction is this special token that's part of its vocabulary. It's this classification token. And so BERT, I'll get into it, the architecture in the next slide. But so BERT is given a sequence of tokens, a sequence of words, and next to each one, and then at the beginning of each sequence is this class token. And so this class token, the role of this token is to absorb information about the corresponding sequence while it's being processed, such that it will serve as a summary of information describing the sequence. And so with each layer of the model, it draws upon the context, the corresponding sequence, and pulls in information that will be important in making this next sentence prediction. So we basically just view it as sort of a summary of the sequence that was being processed. And so that's the basis for the NSP prediction, as well as when you fine-tune this model to make, say, sentiment analysis predictions, this class token will learn to pull in information about the sentiment of the language that it was given, and then you could use that to make predictions about the sentiment of the text. And so those were that's a bit about how BERT functions, and then what about the underlying architecture that allows that to happen? And so this is kind of described by the words on the end. It's the so the architecture of BERT is a bidirectional transformer. And so the transformer architecture is based like almost completely on attention. And what attention does, I will get into it in a minute, but it basically allows the model to tend to different parts of the input sequence when it's processing, say, a masked token or the classification token. These attention modules allow the model to selectively tend to different parts of the input sequence. And so then bidirectional basically just says that when the model is processing a certain token, it can see the text that came before and after it. So this would be opposed to an autoregressive model that only uses what happened thus far to predict what will happen next. So BERT sees the entire sequence. And then something that I think is very interesting about transformers is that they are used to process sequences of things. That's a common application, so a sequence of words as language. But there's nothing inherent in the model that gives it that sort of sequential nature, or there's no like recurrent nature. I don't know if anybody in the audience is familiar with like an RNN, where you explicitly, give that recurrent nature to the model. It explicitly, brings stuff from the last time step towards the next. But BERT processes everything in one go. There's no recurrent nature to it. And so how we instill that sort of temporal nature into the data is through what is called additive positional embeddings. And so there's one embedding, an input embedding that the model learns for the different tokens in its vocabulary. So my dog is cute. He likes playing. So those are tokenized, and then there's an input embedding, for each of my and dog and is and cute. And then that is added to segment embeddings. And so these embeddings denote which sentence BERT was given, if it's given two sentences. So there's the A and B right there. And then within those two sentences, we further have these position embeddings, which denote which index of the input the model or this embedding is present at. And so, so this is the way, the model, these are embeddings that the model can learn, these segment and position embeddings. And so that's essentially how the temporal or the recurrent nature is instilled into this model. And I thought that was really interesting that they process sequences, but there's nothing inherently sequential about them. And so this gentleman, Jay Alomar, has a really good resource on, it's called the Illustrated Transformer. And so he has a great resource. There's no reason for me to recreate the wheel here, but he provides really good visuals about how the transformer architecture works. And so in this case, it shows an encoder-decoder model, but BERT is just an encoder. But so this sort of shows the attention in the transformer that underlies the architecture. And so the model is made up of these transformer layers, and there's inputs to each that the model learns input embeddings, and then with each layer of the model, it will refine those embeddings that it was given based on the context in which they appear. And so, like I said, the self-attention is what allows the model to create those refined embeddings. And so this, I think, is a really good, visual of, how the attention works and how it allows the model to selectively tend to different parts of the inputs when it's processing it. And so here it's, in the fifth layer of this model that he's working with, he's showing the embeddings in the context that the model draws upon when creating the new embedding for it. And so it intuitively makes sense. The animal is where a lot of the attention is focused, and that is that's what it is in this situation, is the animal. And so there's obviously some math behind that allows that to happen. And so this attention works through what is called query, key, and value vectors. And so with each embedding is passed through these query, key, and value vectors. And in the query vector, sort of how I conceptualize it, is that when the model is, say we're working with it, like in the example above, the query vector kind of describes what the model is looking for at that index that it will use to refine the embedding. And then the key says, this is the information that I could provide to embeddings in the context. And then the value is sort of like the payload for that key describing what it could provide. It's that value that it provides. And so there's, it's the query and the key value are multiplied together, and you get value, and then it's softmax to convert to probabilities, and then take a weighted sum of those value vectors according to the softmax probabilities, and that gives you the z-score, and the z-score is what you add that to the original embedding to refine it with each subsequent layer. And so obviously, there's, maybe not obviously, but you can use multiple attention heads, and so the model can learn to pay attention to different things. So different attention heads serve different purposes. I think following with the one from previously, this one orange head, when you're forming it looks at the animal, which is what it is in this case. But then there's also significant attention on describing it. It was too tired. And so it's not only does it allow the model to function, but there's also some interpretability provided through these these attention models. Let me see, there's one. Maybe not. Maybe I'll just move on. Oops. Sorry. One sec. All right. And so that is sort of just like at a high level what the transformer architecture is. And so the transformer is the underlying architecture, and then BERT is specifically pairing that architecture with a specific training regime to train it to understand language. And so then the next area, or the next recent work from machine learning that we take advantage of is this idea of self-supervised contrastive learning. And so similar to how BERT, the goal was to produce, or how it functioned was it gave encoded representations of text. A lot of computer vision models, their core functionality is they provide encoded representation of images. And again, we can sort of tease apart this method, the name of this method. The first part of the method is self-supervised learning. And so in the traditional machine learning setting, or at least I think the one that is most often talked about, is the supervised machine learning setting, and where you have the input you want to give the model and the output you want the model to give back to you. And so then you can correct the model's weights by comparing what it gave back to you with what you want it to give you. And that's the supervised setting. But it's not always the case that we have the labels. The amount of unlabeled data in the world vastly outweighs the amount of labeled data. And so it would be really good if we could learn from unlabeled data. And so that's essentially what self-supervised learning is. It refers to a family of methods for learning from unlabeled data, like learning from the data itself. And then the next part of the name is this idea of contrastive learning. And contrastive learning is essentially like a high-level guiding principle that for this representation learning model, similar inputs should induce similar outputs. And so if I just had this whole spiel about how, we're learning from unlabeled data, how do we know what's similar and what's not? they don't know, but there's a trick that they can do that gives them similar records. And so they don't know, different image to different image, how they relate to one another. But their assumption is that if we have this anchor image, which is this cute little puppy there, if we want to get a similar record that should be described in a similar manner by our model, all we have to do is take a random subcrop of that anchor image. And so then that's what we refer to as the positive in this case. And so when you present the model with the anchor image and the positive, or two positive records for that matter, the model will be encouraged to describe them similarly. It'll output, again, a vector, a set of numbers, and that's what's visualized with a gray dot there. We don't really care necessarily what exactly those numbers are, but we care about the relation between those vectors, and we want the positive and the anchor to be similar to each other, and then dissimilar from crops of other images. And so it's not always the case. Maybe there's a case that a random subcrop of an image is very much different to the original image, but in the long run, it's they've found that this provides enough signal. Yeah.
So I understand that you can take the subcrop of the anchor to make it positive, but where are you getting the negatives from?
So those you just sample from your other images that you have.
So how do you know they're not going to be dogs?
They might be, but they're going to be different from the other ones. There is another dog down there. And so you see that it is, and this is, of course, a toy example, but there, we would expect then that it would be similar to the other dog, but it's, a different type of dog. So it will be different, but in this vector space, yeah, we expect that relation to hold. Yeah. And so we basically, put these together into a method which we call describing player form. And so those of you familiar with European soccer, or I think cricket too, maybe you're familiar with the saying, form is temporary, but class is forever. And so class is sort of like, the general skill level that we prescribe to, say, our favorite athlete. But then, the form is, means to evoke sort of the peaks and valleys in this player's performance over time, the short-term impact of the player. And so that's where we, pull the language of form from. So as you might have guessed, we want to use a transformer architecture. We're going to train a transformer architecture to understand the game of baseball as a sequence of events, using BERT as inspiration as it understands language as a sequence of words. And then use findings from the computer vision community to formulate our own, self-supervised contrastive learning problem that our model can learn useful embeddings from. And so to collect our data, we use the, so our data is originally recorded in the stadiums by Stackcast, but we make use of this PyBaseball package. It's a very good resource. It'd be really nice if other leagues had it. I don't know if anybody wants to do that. NBA data is encouraging or interesting, and football data, but that's one of the reasons we looked at this data is that we looked at baseball is just because the data is so available. And so we pull from there and then populate a local SQLite database. Nothing really crazy going on there. We pull pitch-by-pitch records from over this 5-year period, 2015 to 2019, and then we pull season by season, like historical records describing player performance back to 95. And so ultimately, we create one JSON record for plate appearance. And so, so like I said, this PyBaseball package provides the Stackcast data, which is this play-by-play data. And there's 3 keys that we use to completely reconstruct the sequence of events. And so that's the game PK, which is the like a unique identifier for each game played in the MLB. The at-bat number, which is the at-bat within the game, and then the pitch number, which is the pitch number within the at-bat. And so, using these 3 values from the Stackcast table, we can, completely reconstruct the sequence of events in the MLB games. And so then also in here is the the ID for the batter and the pitcher and the name. And so then we can use that data to describe how the players taking part in this specific pitch have historically performed and have historically matched up against one another. And so we use that data to create one at-bat record per at-bat in the MLB. And so this at-bat JSON contains the information describing the game state at the start of the at-bat, the pitcher and the batter stats historically and among the matchups between them, and then also the the thrown pitches that constitute the at-bat and the result of the pitches. And so our model understands the game as a sequence of pitches, and we describe the result of each pitch with what we call a game state delta token. And so the game state refers to the ball strike count, out count, run count, and the base occupancy. And so then the game state delta describes a change in any one of those components. And so the result of any pitch in the MLB can be described by one of our game state delta tokens. We include the special class token, like I introduced with BERT. It'll serve the same purpose, and I'll expand upon that when we get there. And so in total, there's about 325 tokens that our model learns to understand baseball through. Not all of them are used, which isn't really a problem, just because of how it works out on the back end. But we wanted to restrict ourselves so it's not, it's more interpretable for us. And so then the game state deltas is the predominant way in which we describe what happened on the field to our model. That's the sequence of events the model learns to understand. But we supplement this with, like I said, the information from Stackcast describing the thrown pitch and the batted ball, the pitch type, location over the plate, speed, and then if the ball was hit, how hard it was hit, where it was, which angle, X and Y. And then we also add information describing, like I said, the historical matchups, and then we let the model learn a little embedding describing the stadium in which all of this takes place. And so, visually, the game state delta, for sake of presentation, looks like a small part of the data at each index, but in reality, the game state delta token comprises about half of the data at each index. And so that is the sequence of events that our model, that's essentially like high level, the sequence that the model learns to understand. And so similar to BERT, we use these additive positional embeddings to instill some sort of temporal nature into the model. Slightly different, but still intended to serve a very similar purpose. Here, we have additive embeddings describing the at-bat number and the pitch number. And so we have, the original input sequence, which I showed was the concatenation of that stuff. I just showed the game state deltas there. But once we have that input embedding, that embedding describing whatever happened during this pitch and who was involved and what have you, then we just add these two embeddings that the model can learn to, show the model where, this data is temporally related to one another. And then, similar to BERT, again, we train the model to perform two complementary tasks, very much inspired by masked language modeling that BERT learned to perform. We train the model to perform masked game state modeling. And again, we, similar to BERT, we hypothesized that this would teach the model more about, the micro details of the game, about the tokens, or about the pitches in this case, the events, what they mean for the flow of the game, as well as some rules of the game. And then this self-supervised contrastive form learning objective, which I'll introduce shortly, that encourages the model to derive some sort of embedding describing the emergent meaning from a sequence of these plate appearances. And so for an example of the masked game state modeling objective that the model performs, again, like with BERT, we'll mask 15% of the tokens and then ask the model to predict what was there. And so in this case, it's a 7-pitch at bat with a mask present at the 5th index. And so, when making a prediction for what this masked token originally was, the model first probably realizes that it's not a plate appearance ending event because it can see the entire sequence. It sees that a single happens shortly. So the model should realize that it's a pitch of some sort. It's a ball strike or a foul tip. But then the model should quickly realize that there's already 3 balls in the count, and so it simply can't be a ball. Otherwise, it would either be a 4-ball count, which is just invalid, or a walk, which we know it's not a plate appearance ending event. And it can't. And under our problem formulation, you can't have a foul tip unless you already have 2 strikes. So in this situation, that mask, has to be a strike. But I keep shocking it, I think. But then it's not always the case that there's only going to be a single candidate. And so this is an example of, say we're processing a sequence of at-bats, and this is, say we're modeling a batter. And there's obviously going to be more tokens masked in practice, but here there's a mask at the last event of the 4th at-bat. And so again, there's going to be multiple, events that could fill there. There's no sort of requirements that token would have to satisfy, but the model can look at the context and use the context to try to make its best guess possible. And so, maybe just like how that might happen is that the model can look at, the result of the 3 previous at-bats, and it'll see that it was a strikeout, a home run, and a strikeout. And then the model also sees that there's a lot of foul tips in this sequence that it's processing. So, I think that those probably suggest, a batter that likes to swing a lot, maybe swinging for the fences because he has the home run there. And so, maybe in this situation, the model's not guaranteed to get it right, but I think a good guess based on the context would be perhaps a strikeout or maybe even a home run. But in this case, since there's already 2 strikes, maybe we'll just, say strikeout. And then, say we're processing a sequence of at-bats for a pitcher, and again, there's, the first pitch of the at-bat, there's no, requirements this token will have to satisfy, forward-looking to the end of the at-bat. And so there's multiple candidates, and the model will draw on the context to make a good guess for what was originally there. And so, I think maybe in this situation it'd be reasonable that the model sees that the previous 2 at-bats started with strike. So maybe in this case, so maybe the pitcher, often throws a first pitch strike, what have you. And so maybe a reasonable guess here would be strike. And so in this way, the model, learns to evaluate the context that it was given when making predictions as to what these masked indices will be. And this really teaches the model, to understand the rules of the game as well as how they relate to one another. It's, the micro-based objective. And so we pair this with the self-supervised contrastive form learning objective. And if you recall from computer vision when I introduced it, that the assumption was that 2 subcrops of the same image should be described in a similar fashion. And so then our assumption here is, similar, I think, which is that the same player at 2 close points in time should impact the game in a similar manner. And, kind of like the one guest was getting at, it's not always going to be the case. Maybe you'll get unlucky. But we thought in the long run, over thousands of training examples, we thought this would work out. And so we set out to devise a method for doing that. And so I will obviously describe it in detail, but like a high level, how this manifests is that we say for a given player we want to describe, what we do is we identify a window of activity, and so that window is n consecutive plate appearances, and then from this window of activity we derive 2 views of M plate appearances, and so in our case, we just took the first M plate appearances as view 1, and then the final M plate appearances as view 2. And we assume that M and M are pretty close, so there's a a good amount of overlap there. So not only are these two records showing the same player at two close points in time, but a lot of what they're seeing is very similar. And so then, once we have these views, we ask the model to describe views from the same window of activity with a similar vector, and then ask it to describe views from different windows of activity in a different manner. And so then I think this is just a visual describing that. And so you'll see, so these are color-coded by player. We have 20 plate appearances per player, and then so that's the window of activity, and then we get two views of 15 plate appearances. And like I said, next to each one, we concatenate this classification token, and it's the special, same as BERT, while processing, it'll learn to absorb information from the context that is useful, and, performing the contrastive form learning objective. And so it'll essentially, while processing, it'll pull in information, summarizing the sequence, and then once processed, we use that as the basis for projecting this form vector. And I have the actual loss equation given at the top there, but essentially like I said, how contrastive form learning works is that you encourage similar records to have a similar embedding, so you maximize the similarity between form embeddings from the same window of activity and minimize the similarity of form embeddings from different windows of activity. And so we view this as encouraging the model to learn the emergent meaning from a sequence of plate appearances. And so we thought that this would encourage the model to look at characteristics of how players go about inducing these events. Would a batter battle back from pitchers' counts, or how are the pitches sequenced, and how does the batter respond to those and how does the batter respond to those different sequences of pitches, and how does the batter respond to pitches over different parts of the plate? So not only the types of events that they're inducing, but the manner in which they induce them. Yeah. Sure.
So just to be clear, so CLS2 in this slide would be the output of BERT from that iteration for the sequence of 5 through 50, PA 5 through 20.
So class token 1 through 6, they're all the same to start. It's the same input class embedding. And then while being processed by our model, since we use that token in a specific way, we basically instill that sort of behavior into how the model treats the token, where it draws in the summary information about the corresponding.
CLS1 through CLS6 are actually identical vectors.
Right, to start with, they're identical vectors, but then based on the context of the plate appearances corresponding in the input record, the model will put different information into that class token.
Into each one they'll be different.
Correct.
But then are they mainly a function of 5 through 20 in that case, or is it just?
Yeah. Yeah. Sure. And so that's essentially how we train our model. I make all of the we participated in the open source competition, so I make all of the code available in this repo, and so I will go through some of it. But so this will create basically just reproduce the paper or the models as they were presented in the paper. And they'll produce, different visuals and whatnot. And so the steps will reproduce, the fetching of the data and the, creating the data set and the training records and training the models. But I do provide those for you if you don't, want to do it, or you do need some compute power to train the models. So we do provide the data there, and then the pre-trained models are in this directory here. But so I figured might as well go through some of these scripts that we provide, and then maybe look at some of the code. So there's basically 7 key steps into implementing this pipeline. It's fetching the data, preparing the training records, training the model, and then the rest of the steps are essentially just using the model in different ways. And so the first few steps I probably won't spend too much time on unless anybody has a specific question. It's just sort of fetching the data and populating a local database. I did try to expose as many of the more important parameters in these bash scripts, so you could sort of maybe tinker around if you wanted to without getting too in the weeds. Yeah, so these first scripts just essentially fetch the data and create the database. And then here we pull from that database of Atbat records to actually create the JSON files. And so first we create the Atbat records, and then we create the, we basically just identify the sequence, the consecutive sequences of plate appearances that all players in the MLB over this time period participated in. And so we use that when we draw, when we identify the windows of activity that we will use to describe players. And then here we create whole game records. And so they, like I said, they describe the players in the starting lineup, where this takes place, the home and the away teams, and the statistics of the starting lineups. And this comes into play when we do the downstream task of predicting the winner of a game using these vectors. And so here is where the actual, I think like the novelty comes into play. So this is where we actually train our model. And so I provide two scripts for training both the batter and the pitcher model. They're basically the same underlying architecture, just a few different parameters changed. And so, again, I tried to expose a lot of the important parameters, and I thought maybe I'd talk about them. So the view size and the view length define the number of plate appearances that are considered in a form, and then the view length is the number of pitches in there. And so these are essentially just things that help when we're sort of computationally modeling and creating our data. And then end layers and end attention actually define the transformer model that we train. And so the layers is obviously a number of transformer layers, and then the end attention is the number of attention heads that will be present in each layer. And then the projdim is the dimension of the form embedding. And so in our case, we used 64. And so had an interesting talk with another attendee yesterday, and the sort of the trade-offs with this projection dim. And so like I said, this defines the dimension of the form embedding that we use to describe players. And so, the bigger this embedding is, the more expressive the embedding can be, the more information it can hold, kind of. But since, since in the contrastive form learning objective, each embedding must be compared with every other embedding. It's like n squared memory space, and so that can eat up a lot of memory on your GPU, which is pretty expensive. So the smaller the form dimension, the more records you can fit on the GPU at a single time, but maybe the less expressive it would be. And so we just we didn't do too much experimentation there. We just figured 64 would be a decent estimate there based, just some domain knowledge. Yeah, and so some other parameters there. And so I think one thing that's important to highlight is that you're more than welcome to go and train these models on your own, but you do need like a substantial amount of GPU horsepower. Like these models were trained on cards with 32 gigabytes of RAM, and so that's pretty big. And those GPUs are quite expensive. But that's for the training phase. But once the models are pre-trained and I provide these training weights, and the pre-trained weights, you only need a GPU with about a gig or two of RAM to actually run the models and make use of the embeddings. Yeah, and so the next slides are, or the next scripts are just, leveraging the embeddings. And so this script, describe player form, you give it a checkpoint, a pre-trained model that you want to apply in the directory to the Atbat data, and it'll, go ahead and do it and output one numpy file for each embedding. The next script will go through and aggregate these embeddings by player, and then create some visualizations, just describing how these embeddings relate to each other in space. And so these are obtained with what is called TSNE. I forget exactly what it stands for, but the S is stochastic. And so this is a method for creating lower dimensional representations from high dimensional data. It's very similar to PCA, if you're familiar with that, but I think it basically just works better with higher dimensional data. And so I mentioned the stochastic part because so every time you run it, it's not necessarily going to reproduce this plot exactly, but it'll be similar. And so that's that part, and then this one is, the next script is, instead of aggregating those embeddings by player, what if we cluster them? So these are embeddings that describe players at game start time. What if we sort of cluster them to get some sort of idea about how players form change over time, and just maybe how players develop over time, that'll do that for you. Again, this requires a lot of RAM to do. I forget how exactly much it required, but it was hundreds of gigabytes of RAM. So I may not be doing this for much longer, as we include more seasons and everything, but that's something else that we provide there. And then the next scripts are just are trying to predict the winner of a game using traditional sabermetrics, sort of team level statistics describing teams, run differential, win percentage, things like that. And then it describes the teams using form vectors as well, created by our models. And then the last part, just, you can explore how different, machine learning models take advantage of, the form features. And we ultimately see that not all models, immediately take advantage of the form features, but we see that the random forest model does, and of the 20 most important features to the model, 9 of them were form features, so that was encouraging to us. So I think that wraps up everything I had planned. If anybody has any questions, I'm more than happy to answer them. Yeah.
So basically including the form data, basically improve the prediction accuracy by 1%, like the last time, right?
Yeah, and that's, I think, I would imagine that a lot of companies have sort of in-house, estimates or in-house models that make these predictions and, maybe don't share everything. But that was the best that was published in the literature. And so we took that as a good sign. And then, it wasn't, ultimately the goal of the model, but showed that could be used for that. The embeddings could be used to that end. Thanks. Yeah.
So what you were talking about, you were saying that in order to train these models, you need GPUs for that?
Yeah.
It won't work on ordinary CPUs?
So it can, but it would take forever. You could do inference. I'm not exactly sure how inference would go on a CPU. It would be much more feasible, but would still be longer than using a GPU. Yeah. Yeah, and so I definitely think this can be adapted to other sports, this sort of general framework that we have here. I think obviously baseball lends itself, like I was sort of hinting at, it's a very discrete game. It has a historical emphasis on record keeping and statistical analysis. And so I think basically I want to build models that understand the games as a sequence of events. And so it's just a matter of presenting the model, that data, in the appropriate manner when you apply it to these other events. So, it would be a sequence of plays in the NFL, and, there'd be runs and passes, and there would be, ideally, we would like to incorporate the data from the in-stadium sensors, how, it was a 24-yard pass, how fast was the ball thrown, how fast was the receiver running, how close was the safety or whatever to the wide receiver when the ball was caught. I think it would be I want to build a model that will understand the game through a sequence of events, and then using the model that understands that game, we can look at specific plays or specific plays and see maybe which plays are more similar to one another, or which plays were super influential in changing the trajectory of the game. Very big picture. I envision it being used somewhat how BERT was used. So we'll build these models that have a general understanding of how the game progresses, and then we could fine-tune them for specific in-game prediction tasks. Like the work I'm working on, now the next step of this was predicting, strikeouts and singles and stuff. So first trained the model to understand the general progression of the game, and then fine-tune it for specific purposes. And I think so the general framework, I think, is adaptable to other sports. It's just a matter of, formulating the problem correctly. Right. Yep. I'm going to go to him. Yeah? Yeah.
I know in the beginning you mentioned there's probably some applications for gambling, but could you see this being something that a coaching staff could use maybe to determine, how quickly they're subbing out a pitcher, or just structuring their bullpen, something like that?
Yeah. I think... Yeah, so I think this model, like I said, it understands, or it's intended to understand, how the game progresses and how the events relate to one another. And so obviously, I don't know, there's a question of feasibility, but then I also don't know how much like electronics, the managers and stuff could use in the dugout. So I think we could, off of this, super high resolution embedding, we could carve out like rules of thumb maybe that we could give to the managers, and hopefully, if you see the pitcher, doing X, Y, or Z, maybe that's a sign that they're, what's going to happen in the future. Yeah. Thanks. Yeah.
Well, I want to continue along the angle he was talking about, right? You're talking about like the pitcher getting subbed out, and I was thinking about that in the context of this model here. And this idea, the way you've constructed it, the idea here, right, is the red ones are the same player, the white ones are the same player, the blue ones, and we're trying to make it, hey, the form of this player should be assumed to be more or less constant across these 20 records. And so, so that's why you get the max, the goal is to maximize form 1.form 2, minimize form 1.form 3. But if you were talking about in the context of a pitcher at the, the beginning of the game, his plate appearances 1 through 15, and then his last 15 plate appearances, I wouldn't expect his form to be the same. And so, like, how does that jive with this approach?
So, you're talking about like the differences within game? Yeah. So I guess I forgot to mention that. So for batters, we assume 15 plate appearances describe their form. And then for pitchers, we use 60. And so both sequences for pitchers and batters describe, a handful of games. And so the model, it should see, the general nature. Yeah, it's like general form over the short term, maybe. Right. Yeah.
When you started, you were talking about the traditional stats that are used in baseball. Have you inferred any new insights, any new stats just from the data and what you've seen?
No, I actually, I personally have, I've sort of moved on to the next next phase of this work, but I'm working with an undergraduate at Penn State who is looking at the different forms that we cluster these players to, and trying to prescribe some sort of meaning with that form, and trying to tease out maybe a new statistic or what have you. So we're working on that. We're just nothing to share yet. Yep. All right. So thank you guys for joining me today.